Hello, everyone. My name is Kia, and today I'm so excited to discuss our recent research titled Domain Adaptation Using Optimal Transport for Invariant Learning Using Histopathology Datasets. This paper sits at the crossroads of medical imaging, artificial intelligence, and machine learning, addressing one of the key challenges in the field of computational pathology, which is batch effect. The term batch effect may vary in definition across different fields. In histology, it refers to variations in the appearance of images between different institutions. These variations can stem from differences in tissue preparation protocols, scanner types, and other factors. These batch effects may not significantly impact the pathologist's diagnosis, but they can drastically degrade the performance of a machine learning model. Imagine a model that performs exponentially well with data from one institution, but falls short when applied to data from another. This highlights a crucial problem of generalization. One might suggest addressing this issue by incorporating images from new institutions into the model's training and learning process. However, this approach has its own drawbacks. First, it can be very costly, as we all know that annotating medical data requires board-certified experts. Secondly, given the countless number of institutions globally, it's not feasible to include data from all of them. Therefore, we need to devise a different strategy to mitigate these batch effects. In our research, we explore one such potential solution.
Now I'm going to talk about optimal transport. Optimal transport has been introduced by Gaspard Monge in 18th century. He asked a simple question: how can we optimally transport dirt from one location to another one? This simple idea created a formulation for measuring distance and transferring different probability distributions. Basically, we want to find the gamma, which is the coupling matrix for the mapping, in a way that minimizes the cost function C. And remember, the constraint set pi enforces gamma to be measure preserving. Solving this equation can be very costly and expensive, and there are multiple ways and multiple algorithms to do this. We want to solve our batch effect problems using optimal transport. Our approach is that instead of only using cross-entropy loss for training, we add an optimal transport loss or OT loss. The contribution of OT loss is being determined by alpha. We apply OT loss to the feature map of train and validation set. The goal is to regularize the feature map and make it domain invariant. Remember, the labels are only from the training set. We only use validation set for the OT loss. And we test our model on a completely different institution. In this slide, I'm showing the results of our OT regularized approach. So the table here shows the accuracy for validation and test set for various alpha value. The numbers are mean and standard deviation over 4 experiments. And we have achieved the highest accuracy for validation set when we set alpha to 0.1. And this will give us roughly the highest accuracy for test set as well. And by comparing with the baseline methods, our framework outperforms baseline by approximately 3% and 15% for validation and test set, respectively. Here, I'm showing the domain distribution before optimal transport. So on the left, you can see the training domain, validation domain, and test domain. And then on the right side, it's true positive, true negative, and false negative. As you can see, before OT, there is a separation between each domain, which represent basically different institutions. After OT, we can see that the train, validation, and test set are blending together and they are closer together. So the model that are being trained on any of these institutions will be domain invariant. In conclusion, we developed a deep learning framework based on optimal transport to overcome batch effect. And our results show improvement in accuracy up to 15%. Thank you so much for your attention, and I hope you enjoyed the conference.